Hello, welcome to Code Alibaba. We will see the 8 code problem now. It is the shortest path visiting all nodes. Okay, so it's a hard problem of the code. It says you are given an undirected connected graph. Yes, so it is connected. It is not having any. It is not having any components on it. It is a single component graph. The nodes are labeled from 0 to n minus 1. Oh, yes, we are labeled from 0 to n minus 1. And you are given a array graph. The graph is a list of all nodes connected with a node I by nh. So n is even return the length of the shortest path that visits every node. Return the length of the shortest path that visit every node. Return the length of the shortest path that visit every node. You may start and stop at any node. You may revisit nodes multiple times and you may reuse the edges. Return the length of the shortest path. Okay, so length of the return of the shortest path that visits every node. The shortest path should visit every node. You may start and stop at any node. You may revisit node multiple times. You may reuse the edges as well. Hmm. What the problem actually says, I'm also a bit confused. It's a kind of ambiguous statement. Okay, nevertheless, let's see this example. It's the graph uh, which is having 1, 2, 3. Okay, so 0 is having the connection with 1, 2, and 3. Okay, as see here. The 1 is having connection with a 0, 2 is having connection with a 0, 3 is having a connection with a 0. Cool. Undirected nature is undirected nature can be seen in this example. Right. Now they say the answer is 4. So the length of the shortest path that will visit every node is 4. Now how? That's the main question. They say one of the path is this. Uh, they say the path should be this. They first visit the 1, then 0, then 2, and revisit 0, and this. Cool. So they exclusively they have said exclusively that you may start and stop at any node. You may start and stop at any node. Okay, if I take the general example of this, if I start from 0, let's say we start from the 0, we visit 1, it's distance 1, we again visit 0, it's 2, it's 3, it's 4, it's 5, it's 6. So can you see the answer is 6, not optimal. If we start from the 2, let's say 1, 2, 3, 4, 5. Again, not that optimal. 3, visiting 3 just now would be not good. So let's visit 2. 2, so it's 1 plus 1, 2, 3, 4. Okay. It's not necessary that I come again to that particular node. Over here, 3 is the example. It means that even if I simply start from 3, I have visited 3, I have visited 0, 0 is visited once, I have to visit 2. Okay, let's visit it. 3 is already visited. No need to visit it again. I have to visit 1. Cool. So what is the path? 1, 2, 3, 4. 4 is the answer. If I try to draw another path from this 2, 2 is visited, 0 is visited, no need to visit. Answer is 1 up to now. Answer is 2. Answer is 3. Answer is 4. Again, the answer is 4. And everything is visited once. Cool. Okay. Let's see this example. I think it's kind of it will give us more insights about the problem. Okay. Again, we have the answer 4, but how? Uh, they say the one of the possible path is 0, 1, 4, 2, 3. They say that we should start from a 0 and we should end up to a 4. We will start from a 0, go all the way down to 4, go all the way down to 2, go all the way down to 3. See, I have visited all the nodes and my answer is 4. If I take some other path in this case, if I go this, if I do this, I can go, but what should be what would be the answer? 1, 2, 3, 4, 5, 6. 6 is the answer. I don't think that's optimal for sure. Cool. If I start from this fellow, 3 is visited, 1 is visited, 4 is visited. No, it's a cycle. It's a cycle. It no need to go in the direction. It can go over here only. And this. Now what is the answer? 1, 2, 3, 4, 5. 5. It's again not optimal. We know the answer is that only we are trying out each and every possibility of what would happen. If we go like this, then this, great. We have noticed one thing. Uh, it's just an initial observation. If we don't have a cycle, we can visit in any order. Whether we can start from a two, whether we can start from a 0. I think 0 is not optimal, right? The answer from so if we start from 0, I visit 1, I come again to 0, I visit 2, I come again to 2, I visit 3. What is 1 plus 2 plus 3 plus 4 plus 1? 5. Not optimal. We have to start from the ends only. Okay, okay. First of all, if I see the constraints, it's 12. Very small constraint. I just mean to say that maybe we have to try out all the ways. Maybe we have to try out all the ways. What's the important condition? What's the important condition? The only condition that is needed is every node should be visited. Every node should be visited. It's not said that we can visit a, we can visit a, let's say, we have visited 2 or we have visited 0 already. It don't say that you cannot visit 0. First of all, this is one of the initial observation. One of the initial observation. Uh, and everyone have to be visited. So at the base case, we can apply the checks. At the base case, we can apply the checks as needed. Uh, so Cool. At the base is written up in the checks needed. Uh, if I do something like backtracking, if I do something like backtracking, what it could be. If I'm at a particular node, first of all, I'm at a particular node. It says you can start and stop from anywhere. You can start and stop from anywhere. So it says we have to start and end from anywhere. Now, it doesn't matter that base case would be base case would be that whether I have visited all the nodes or not, whether I have visited all the because there is no certainty that you have to stop over this particular node only. You can stop anywhere. You can stop anywhere. It may happen that I visit this four and somehow, somehow I have done the traversal and have come to four. It only needs to be checked that four is visited once. Um, okay, so sorry for the interruption. Let's again try out. Cool. So we notice that we at the base case we have to see whether all the nodes are visited or not. And uh, when I say when I say that the all the nodes are visited, I need to have some variable which will define. I need to have some variable which will define that this is the number of steps that you have taken to initialize your answer from that very starting node. To initialize your answer from that very starting node. If I start this traversal from 3, I need to have a variable which will be initially initialized as 0 because it will only contain the number of steps that are taken to reach the answer or to reach the state in which all the nodes of the visited, all the nodes are basically visited. Cool. So if I somehow kind of write the DP state, what would be? I think, yeah, we need to go towards DP, not specifically DP, but rather what I say, backtracking kind of a thing. Okay, let me just kind of try out. Uh, my function would contain uh, current node because at least I need to know where I'm currently standing in order to access the neighbors. One of the things is this. Cool. Uh, I need to keep the visit. This would be the second condition. And again, I need to have the distance. Cool. Yeah, I think this much of information is needed. And over here we can have the base case. It will just check all if all the 12 nodes are visited or not. If they are visited, I can return the answer. Rather, I can keep the variable and I can keep the you know what? You know what? I will return. This function would be it will return an integer. It will return an integer, and that would be the answer, the minimum answer which we all are trying to find. So it will return the distance. Cool. Now at the transitions, what I will exactly have for basically for auto IT for all the neighbors, what I will have, there's no restriction on the visited. Basically over here I can declare the base variable answer as int max. I will declare the answer as int max and I will compute the answer from all the IT that are going away. And before calling the function, I will mark them as visited. Let's see whether this idea works or not. Actually, yeah, cool. Let's start down. Let's just clear it off and try to write the code. Uh, First of all, an integer quantity only. This is the current node. This is the current node, and this is the basically the graph is already given to me, right? So I will just get this graph. Ta-da-da, graph. I will have the distance. I will have the distance. Do I necessarily need to have the visited? Yes, I need to have the visited. Okay, let's have the visit. Cool. Let me just keep the code section. I think you'll be able to see it. Okay. Uh, in this, first of all, let me just remember this completion. Mm, Basically, this condition would be for all the nodes. Yeah, if my uh, visitors for all the nodes, if my visit is marked for all the nodes, if I'm visited marked, I will just keep the counter plus plus. I can keep the counter initialized to 0. I will keep the counter plus plus. I will increment my counter. After it, uh, sorry, it will be visited. Okay. Now, after it, I will have the count. If my count is, yeah, so we have reached the base condition. We can simply return the distance. Cool. Now we can keep the answer for all the neighbors. I hope you are following the code for all the neighbors. If the visited can be revisited as well. So there is no restriction whether current IT is visited or not. I will just call this function for all. Let me just keep my answer comma, the function which I'm calling. But before that, let me be sure that yeah, I'm visiting this fellow. Why I'm doing so? Like, I should do this. Let's see if it's correct at the end or not. Yeah, so and also my distance will going to be increased. So item will be called. What are the variables? Item will be called. Distance plus one will be there. Visit will be there. Graph will be there. Cool. And over here it will be, sorry, it will be graph, and then I can return answer. Over here, other thing is this. I just have to uh, make my visitor. It will be a simple vector and extract, and all will be unmarked initially. Wow. Plus plus. Just a hold. I can keep the answer as figure value. Answer would be anyone wants answer, and the function whichever we call it. We will need a visit. Do we need a visit over here? Do we need a visit over here? Yes, I think we need a visit. Cool, 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 cool. Okay, okay, okay. We have to mark out. Notice the distance is there, visit is there, and graph is there. Notice the distance is there, visit is there, uh, graph is there. Now, do I need to have, do I need to have, do I need to have a separate graph, separate vector field created each time, a separate visited? I think I can apply that for here as well. Right. Let's try to work on the same. Uh, see, let's see. Step overflow. Okay, vector image and graph. The problem. Black image. So you vector step overflow on addresses. Cool. So at the base condition, we'll keep the counter. We'll return the distance. Mm, for all the neighbors, I visit them, remove the visit. Stack overflow is there. Stack overflow. So the graph, the stack is becoming overflow. Means we somehow need to we make sure somehow we need to make sure that uh, why we are essentially making it visited and then making it non-visited. It's not the visitor. But the problem is not to travel out. It says current condition. Ooh. Mhm. I have visited it. I have done my job. I've revisited it. I have revisited it. But the whole idea is that when I start from this node, I visit the node, I go away, I come back, revisit, I revisit the node, I revisit the node. First time when I go, it's kept visited, it is kept visited, it is visited, come back, it is again visited. But uh, return the length of the shortest path that visits every node. You may start and stop at any node you want to. You revisit any node multiple times. But uh, we need to somehow stop this incursion from happening. We need to stop somehow. We need to stop this incursion from happening. Somehow we need to stop this incursion from happening. Good. I'm saying this is the base condition. This is the base condition. I strictly have to return. I strictly have to return. Uh, can I keep a global variable and I have to return it? Uh, uh, I guess this is kind of matching. It's one, two, three. Answer is infinite maximum. Um, T line having this. So what type of function? Mhm. Again, we have done something. Again, we have done those. Okay, again, we have a stack overflow. Stack is overflowing. We visit this fellow all the time. Cool. So the solution can be accepted and it's not the correct one. For this shorter distance, we will have to keep the BFS instead of this BFS approach. We will use the BFS and uh, to check faster whether I have visited or not. All the nodes are visited or not. To check faster whether all the nodes are visited or not. It's the fastest way is the bit masking. As this constraint is small and is going only up to 12, we can use a bit mask and that bit mask can easily tell in big O of 1 that whether the graph is visited or not completely. And also, it will give us the shortest distance as well because VFS is bad for search. Cool. Okay. Nevertheless, we found a solution that cannot work in this problem. The solution cannot work. It's also important that you try to fail sometimes. You get to know that this solution doesn't work, that solution doesn't work. It gives you an exposure. Okay, so we will have BFS approach. So what is the first thing we need in a BFS? It's a queue, and I also have to uh, keep that mask along with me while browsing the queue. Queue, mm, uh, uh, we have this number of nodes with me. It's a multi-source BFS. It's a multi-source BFS. Source can be many, which are calling this BFS function. So we can have many. We can have a good number of we can have a good number of sources lying with us. Cool, cool. So this is the solution to this problem. First of all, we have used a mask. Now, where a mask is acting as a state variable because mask will instantly tell me that what all I have visited up to now, what all I have visited up to now. And if I come to a node, let's say I have visited three nodes X, Y, Z, and I have come to node A. Now it may possible that I again come to X, Y, Z and node A. Now that is a state. That is the same state. We can't do recomputation on that because that would definitely give us a stack overflow, right? That will definitely give us a stack overflow. Rather, what we will do is we will create the state. So we will use a queue pair, which will tell me the node and the which will tell me the node and the visited stuff, and I have the visited of a vector which will tell me the node comma mask, right? I hope you understand what I'm trying to say. Cool. Now multi-source BFS as we all the nodes can be act as a starting point, and because of that reason all the nodes are acting as a starting point. All the nodes are acting as a starting point. It means that everyone have to be inserted into the queue. This is the general format of the multi-source VFS, right? So I have pushed these into the queue and I have visited this particular state in which initially this mask is saying that only the ith node is visited initially, and I have pushed it into the queue along with I have marked this state as one. Cool. Now I will keep the distance equals to 0 while the queue is not empty. What I will do is I will get the size of the queue. Now what is representing the size? The size will represent the current level of the nodes. And inside this, I will just simply check if my mask is equals to I raised to the power or 2 raised to the power of n minus 1. It means that are all the nodes visited, I will just quickly represent, I'll just quickly return a distance. Or what I will do next. See, all the nodes of this level are have to be executed out. All the nodes of this level have to be executed out, and then a distance have to be increased by one, because the q state is not distance comma something. So the particular level nodes, so the nodes of the particular level are explored first. What I'm saying, the nodes of the particular level are explored, and they are at the same distance traveled up to now. That's why I'm using the size. This is the current size. For this particular level, we have the distance as dist. Cool. And when I have come to this particular level, I just see if all of my nodes are visited early, then I can simply return this distance. Or else I will, for every neighbor to this node IT, mask will say, yeah, visit it up. Mask will say, yeah, visit it up. And simply, the queue will push back. The queue will push back this particular new state. Mask will helping us in revisiting, and visit is preventing the answer from is preventing from a state getting repeated. So okay, there's a clear difference. Visit is helping us in preventing the states to be repeated, and the mask currently help us to visit all the neighbors. So, we have neighbor 1, we have neighbor 2, we have neighbor 3, we have neighbor 4. All the neighbors will be marked one by one. And also, I will just see if this particular state is not visited, then only I will just enter it into the uh, queue, and I will just do the distance plus 1, plus 1, and at the end I will return a minus 1. I hope you understand the solution. The earlier solution was not working. First of all, it was not guaranteeing us the minimum answer. And secondly, we need a mask to increase the efficiency of the code. Let's try to submit it out. Code, it's got accepted. I hope you understand the solution. Till then, keep learning. Bye.